Welcome back. So let's look at another example of how we can use transfer functions to determine the response of output in response to input changes. We continue with our previous example for continuous blending process, where we have already found our steady-state gain. We want to determine the nominal exit condition concentration bar given all these values. So at nominal exit concentration, we have steady state. At steady state, we have the time goes to 0. At the left, we have 0, and on the right, all the inputs and outputs goes to steady state values. And what are the output? The output is x, is the output. And x1 is the input, x2 is a constant. So we put input and output at steady state. So x1 is the input at steady state, and x is output at steady state. Notice that x2 does not get a bar because it is constant. So we can solve for x bar. We have w1 x1 bar plus w2 x2 divided by w. Now we can plug in numbers. W1 600, x1 bar is 0.05 plus 2 times 1. And w equals to w1 plus w2, because it is the total flow rate. And finally, we get a numerical answer of 0.05. Notice that the unit of kilograms per minute are cancelled from top and bottom, and giving us a composition. Now we want to find an expression for the output response x of t in the time domain, given the transfer function we just solved. Note that the transfer function by definition is the output in the Laplace space. In this case, it's big X of s divided by the input. In this case, big X of 1. Given there is a sudden input change, so it is a step change in x1 from this composition to this composition at t equals 0. Assume the process is initially at steady state, so we have vanishing initial condition and given all these constants. So to get x of t, we need to first go from big X of s. Oh, in this case, we have derived it in the deviation form, the deviation space. Inverse transform it to the deviation space in the time domain, then convert it into the output response. But to do that, big X prime of s can be equal to this transfer function multiplied by big X1. And what is, we already know the transfer function. What is the x1 prime of s? We know that it is the Laplace transform of the x1 prime. And what is x1 prime of t? It has an step input change from one value to another. So it is a constant step increase. It is Laplace transform change from 0.075 minus 0.05. And the Laplace transform of a constant is the constant divided by s. So we have g of s multiplied by 0.25 divided by s. And then g of s is k1 divided by tau of s plus 1 multiplied by the amount of step increase divided by s. Now we want to carefully look at the Laplace transform table and identify inverse Laplace transform of s plus b1 divided by s plus b2. 1 over that is equal to b1 minus b2, 1 over that, multiplied by the negative b2 of t minus e to the negative b. So for the real domain function, we want to take the inverse Laplace transform of the Laplace space function and take the inverse Laplace transform of that. We want to write it in terms of function form that is found in the table. To do that, first take out the constant, which is 0.525 k1. The Laplace transform of 1 over, we want to write s in terms of coefficient of 1, so we divide the top and bottom by tau. 1 over tau, top, and then at the bottom we divide it by tau. S plus 1 minus tau multiplied by s. Again, tau is a constant, so we can take that out. So 0.25 k1 over tau. The Laplace transform of that, we have b1 equals to 1 over tau, and then b2 equals. So we have b1 minus b2 is 1 over tau. Then e to the 0 minus e to the negative 1 over tau t, so t divided by tau. And finally, we simplify it. 0.25 k tau squared, 1 minus e to the negative t over tau. This is the deviation variable in the time domain. So we finally want to write it in terms of the original variable. And the original variable is just the deviation variable plus the nominal steady state, which we just determined. That is 25 squared, 1 minus e to the negative t over tau plus the nominal steady state. And since we're given numbers, let's substitute in numbers. So tau is, by definition, we found before, is rho v divided by w. So 900 times 2 divided by w. That is 600 plus 2, total flow rate. That equals to 2.99. The units should be in minutes. We have 0.25 divided by 2.99 squared. One minus e to the negative t divided by 2.99. Plus the steady state value we calculated in the last section, 0. I noticed that I forgot a k here. Got a k here. Let's put the k back. K is equal to w1 divided by w. That's 600 divided by 602. That is negligibly close to. Let's put that in. Oh. And I claim the results should be 0.0 to 8. 1 minus e to the e divided by 199, 0.0. So in this example, the way to solve it is to transform it from the Laplace space into the time domain, and then finally from deviation variable to the original variable. We solve it analytically first, then we substitute numerical values. If you're following along and actually doing the calculations, you would find that the value I claimed is incorrect. It is not 0.028. It should be 0.0249 because I forgot to include the k. Right? So in this video, we went over an example of how we can use transfer functions to determine output response upon the step input chain. And we made it more practical by getting in numbers, substitute them into the equation we solved for analytically.